Auzubillahiminash-shaytanir-rajim. Bismillahir-rahmanir-rahim. In the lecture series of Material Studio and within the course of hydrogen storage, we are at the lecture number 3. And in today's lecture, we are going to discuss an important part of density function theory results, which is the analysis and interpretation of band structure and density of state. And in the previous steps, we already performed the calculation. Now, in this lecture, we will focus on how to understand and interpret these results physically. So moving ahead towards the analysis of band structure, since we already performed calculation, so we will open the output file of band structure, and after clicking on the case step button, we have two options. The first one is calculation and the second one is analysis. Since we are doing analysis, so we will go with analysis option, and here we have band structure, density of state, elastic constant, and optical properties, core level spectroscopy, etc. So our aim is to make analysis for band structure, so we will must select the band structure. After clicking on view button, we will get our results. Band structure is a graphical representation that shows how the energy of electrons vary with respect to their momentum in a crystal. In simple terms, it tells us how electrons are distributed in energy level inside a material and whether they can move freely or not. It is one of the most important tools to understand the electronic nature of the material. So now when we look at a band structure plot, we must clearly understand its axis. The x-axis represents the k point, also called a vector in a reciprocal space. These k points are taken along high symmetry direction in the breakdown zone, such as x, r, m, g, and r. And these are depending on the crystal structure. So these points are connected to the form to form a k point, which shows how the electronic energy changes along different crystallographic direction. And along y-axis, the y-axis represent the energy of electron, usually measured in electron volt. The energy is plotted relative to the Fermi level, which is typically set to 0. Which is typically set to 0 electron volt, and the Fermi level act is a reference point to determine occupied and unoccupied electronic state. Now, when we analyze a band structure, the most important feature we look at is the band gap. The band gap is defined as the energy difference between the valence band and conduction band. So these band gap determine whether a material is a metal, semiconductor, or insulator. So if there is no band gap, if there is no gap between valence and conduction band, or they overlap, so the material behaves as a metal and shows high electrical conductivity. If there is a small but finite band gap, the material behaves as a semiconductor, and if the band gap is large, and so the material behaves as an insulator. Now, an important concept here is direct and indirect band gap. A material has a direct band gap when the valence band maxima and conduction band minima occur at the same k point in Brillouin zone. So this means an electron can directly jump from valence to conduction band without any change in momentum. On the other hand, a material has an indirect band gap when the valence band maximum and conduction band minima occur at a different k point. So in this case, a phonon is required to conserve momentum during the electronic transition. So this is very important because direct band gap material are very efficient for optical applications, and indirect band gap material are less efficient for light emission but still useful in electronic application. So from the band structure, we not only determine the value of the band gap but also the nature of the band structure, which is very important for understanding material application. Now let us move towards the density of state, which complements band structure analysis. Density of state is defined as the number of electronic state available at each energy level in a material. In simple words, while band structure tells us where the energy level are located. So does tell us how many states are available at those energy level. So in dance analysis, we mainly focus on the region around the Fermi level. So the Fermi level is the highest occupied energy level at absolute zero temperature. If the density of state at the Fermi level is non-zero, the material behave as a metal. And if there is a gap in dust around the Fermi level, so the material behave as a semiconductor or insulator. So does give us another way to confirm the electronic nature of the material. Now we will must analyze the partial density of state, uh, um, which tell us the contribution of specific atom or orbital such as s, p, and d orbital. And this is very useful because it helps us understand which atoms are responsible for electronic conduction and bonding in the material. For example, in many material, d orbitals play a major role in conductivity and chemical bonding, while p orbital often contribute to valence state. So now yes, we will do partial density calculation in upcoming lecture, but here at this moment, now let us connect band structure and task. So we found band structure give us energy variation with momentum, while DAOs give us the distribution of electronic state with energy. And band structure provide directional information in k space, where DAOs provide a global picture of electronic state. Together they give a complete understanding of the electronic structure of material. So in practical DFT analysis, we use band structure to determine band gap type, direct or indirect nature, and electronic transition. Then we use DAOs to confirm the band gap and to analyze orbital contribution and electronic density near the Fermi level. Finally, in material like hydrogen storage system, and perovskite, this analysis become very important because the electronic structure directly affect the absorption behavior, charge transfer, and stability of the systems. So to conclude, band structure help us understand the type and the nature of the band gap, while DAS help us understand the density and contribution of electronic state. Both analyses are essential for a complete understanding of electronic properties and DFT. With this, thank you very much. If anyone have any question, feel free to comment.